Okay, so our next speaker is Tomás Gómez from ICMAT, Madrid. The title is on the board.
Okay. Okay, so first I want to thank the organizers for the invitation to speak here. It is always a pleasure to be here. In fact, last time I was here was 6 years ago, and what I am going to talk about is based on things that I learned in the lectures 6 years ago. So it has been very useful to me for me to come here, and also this conference is being very nice and useful. Okay, so the problem that I'm going to talk about is the constructing. First, I will talk about the principal bundles on higher dimensional varieties. This has been constructed by several people, and I was involved also in this. But then there was one missing piece, that there was no notion of a Gieseker-Harder-Narasimhan for these principal bundles over higher dimensional varieties. You could define slope Harder-Narasimhan or Mumford-Harder-Narasimhan if you prefer, but not the Gieseker. Okay, so then I will start with some the basics. I am going to work always on X, smooth projective variety over the complex numbers for simplicity. Okay, so then first, let's go back for a moment to dimension 1. In dimension 1, we have a Mumford definition of stability. So if you have a vector bundle is semi-stable, so we all know this. If for every subbundle the slope is smaller or equal, I will write it in a slightly different way. I will say that for all weighted filtrations, and by a weighted filtration, I mean something like this. So this is the length of the filtration is T, so T plus 1 is this. If you want, you can make this a strict inequalities, and then there are some weights that are strictly increasing. Okay, so this I will use many times this notion of a weighted filtration, so I write it once and for all. And the definition is that the vector bundle is semi-stable if for every, well, this is weighted filtration. Weighted filtration, I have this inequality. Lambda I plus 1 minus lambda I. Di R minus Ri D. Di is, of course, the degree of its piece. Ri is the rank. D is the degree of the vector bundle, and R the rank of the vector bundle. So if you just take one-step filtration, then this is the usual definition, and of course it is equivalent to checking for all filtrations. Okay. Next, we have Ramanujan definition of semi-stability. Now the object is a principal bundle. For me, G always is going to be a complex, reductive, connected algebraic group. Then now the definition is that for all reductions of a structure group Q parabolic. And for every undominant character, on Q. So I take the reduction using the character, I get a line bundle, then the degree of this line bundle should be smaller or equal than 0. Yes. That's right. So this is why I use Q for parabolic, because E sometimes is a vector bundle, sometimes is a principal bundle. Maybe I should have used a P here, because E in the talk in general is going to be a vector bundle. But well, I won't change it here, yeah. Okay, so then this is the direct generalization of this notion, because filtration is a reduction to some parabolic. And in fact, I think that the story of this, the definition is that Ramanujan was a graduate student of Ramanujan. So Ramanujan gave this definition to Ramanujan, and he told him, let's see what you can do with this. And then he constructed the moduli space and everything. Okay, now let's move to, and well, this is why I wanted to put filtrations, because it fits better with this notion. Yes, you can take them integer. And maybe rational, but you just multiply. This is linear, so yeah, integers. Yeah, well, actually here, maybe, yeah, sometimes it is maybe better that I put it like this, 1, 2, t plus 1. Yeah, there is always some confusion, so you can label them with integer numbers and then use the weights. If you use the weights to label the bundles, then you don't need to add the weights, but maybe this is more clear. Because so this index is only an index. It doesn't appear in the formula. Okay, so for higher dimensions, we have a Gieseker definition, or Gieseker-Maruyama. Well, this is for dimension x bigger than 1. Then here, now I need to fix a polarization, and the definition will depend on this. And then E, a torsion-free sieve, is Gieseker semi-stable if for all weighted filtrations but now these are not vector bundles, these are torsion-free sieves in general. The following formula is satisfied. Okay, now P now is the Hilbert polynomial of E. Pi is the Hilbert polynomial of N. This is why I need a polarization to define this. And this means that for very high N, this should be satisfied. Okay, so then, and then, well, they construct Gieseker and Maruyama, later Simpson. With more generality, they construct a moduli space for these objects, and you get a proper moduli space. So the idea here is that we want proper moduli spaces, projective moduli spaces. And so let's see that there are, going from a dimension 1 to dimension 3, there are, to higher dimension, there are 3 things that have happened. First, I had to consider torsion-free sieves. to get a projective moduli space. The second thing is that even if I am only interested in vector bundles, to check stability, I still have to look at the torsion-free sheaves. This means that, so if you think of this as a reduction to a parabolic, then the reductions that you have to consider are rational reductions. So they are reductions on some big open set, maybe not on the whole thing. And the third feature is that instead of degrees, we have to consider polynomials, right? Okay, so then if we move to higher dimensions with principal bundles, we will expect these three features to appear there. Okay, I will explain in a simple case. Suppose G is the symplectic group. Then a principal SPR bundle, I can think of it as a vector bundle together with a bilinear form. And well, this bilinear form, it should be skew and non-degenerate, right? So if this is a vector bundle, then this is a principal bundle. And here there is something very easy that I can do to get beyond the vector bundles. I can just allow this to be a torsion-free sheaf. Then I give a homomorphism from this sheaf to this. This still makes sense. I can require that this is skew symmetric. And the non-degeneracy, I can define it, so it also makes sense. I can say that this is non-degenerate on the open set where it is locally free, or I can describe it several ways. That is enough, that would be enough. So then this will give a principal symplectic bundle on U that is, well, I call it like this. This is the open set where E is locally free. So to put things in, yeah. And then I have to define a notion of stability. Well, this for symplectic bundles and orthogonal bundles, this was a joint work with Ignacio Sols in 2001. At that time, I was still a graduate student in the IFR. Then, now, postdoc. The postdoc, yes, sorry. I was not that young. Okay, so then the definition is the following. Now I will look again at the filtrations, weighted filtrations, but they have to respect this in the sense that, well, the weights should be symmetric. And EI, the orthogonal of EI should be equal to E T plus 1 minus I, where the orthogonal is defined as the kernel phi sends E to E dual, then this goes to EI dual, the kernel of this composition. And what I have to check is the same notion that for every, so I call this well, weighted symplectic filtrations, then okay. So just one comment. So suppose that I am in dimension 1, then this will be a vector bundle. Then the filtration will be filtration by vector bundles. And then this coincides with the Ramanujan definition for symplectic bundles. And well, this was already studied by Ramanujan. There is in his paper about the orthogonal bundles. And here, so the observation is that the condition is the same. The condition looks the same, but I don't check with all filtrations, only with orthogonal filtrations. And an orthogonal filtration is just a filtration that when I take the perp, this is reversed and it should be the same one. Okay, so then this data here can also be thought as the following. So I have a torsion-free sheaf over X. So this is torsion-free. Then I have a principal symplectic bundle over some big open set U. But I have something else, of course. Then I have an isomorphism between the reduction. Well, I will make this a little bigger because this will be important. This is an isomorphism with well, by this I mean, so what I have in mind. So here secretly I have been using the standard representation of the symplectic bundle, right? So then if I have a principal bundle over U, then I get a vector bundle over U, and I fix an isomorphism between these. So this is going to be the example that can be now generalized to any group. For any group, I will fix a representation. Then a row sheaf. Yeah, well, maybe I will, since this is a definition, this is just a.
I ask what you said earlier is this. So these two kinds of data are the same. So you have E torsion free sheaf. You say P is the SP bundle on an open set, and then the psi is an isomorphism. Yeah, what is PV?
PV, so P is the principal bundle.
Oh,
I will repeat this here.
Okay.
I will repeat this to me. So
but
this is the basic object.
But that's the same thing as having the symmetric.
Yes.
The skew symmetric form on the whole of E.
Yes, because if you are given it on the open set, there is a unique extension to.
So this specifically is like standard representation of.
Yeah, there is the standard representation. So
thank you.
To make things clear, so here in general, I will take G a group. I will fix a representation. Well, this representation should have some conditions. Here, for instance, I want that the center goes to the center of a GLV. Then later on, I can take products of a GLV in case the center is very big, but well, just to simplify. If I have a group and a representation, then the definition is that a principal row sheaf is a triple where E is a torsion-free sheaf on X, on the whole of X. P is a principal G bundle on the open set where E is locally free. And there is an isomorphism between or if you want a P rho or P V, both things mean the same. So you can think of this in two ways. One way that I like to think is that first you are given a principal bundle on U. The principal bundle on U gives you a vector bundle on U using this representation. And this vector bundle can be extended in different ways as a torsion-free sieve to the whole of X. Different extensions will give different points in the moduli space. Okay, so then this is the general object that we consider. So this, with there are many works considering these objects, like with Ignacio Sols. In fact, we consider the adjoint representation. Then, because the adjoint representation does not satisfy this, then we have to do something else. But just to simplify, I'm considering this. Then this is also considered by Schmidt, and then together with Langer, Schmidt, and Sols, we have some papers on this. And then,
in this example, which representations can you take to recover?
Yeah, here I am taking the standard representation.
Yeah, but which other ones you could take?
Sorry?
Which other ones could you could take? Faithful or what?
Yeah, some faithful representation. Yeah, here it is. Yeah, as long as it satisfies this. But I guess I don't know if it is very interesting to consider also others. Yeah, maybe if you consider the dual representation, then you will get a different compactification. Yeah, this is something that, so we construct a modular space for this, but then the compactification depends on the representation that we are using. So this is a feature of this approach. In dimension 1, of course, it doesn't. The modular space doesn't. Yes. It's U is the place where the torsion-free sieve is locally free, so the complement has a codimension at least 2. And so an open set whose codimension has whose complement has codimension at least 2, I call it a big open set. Because, so you can calculate the degree there, for instance, and yeah. Okay, so then now the definition is the following. So I will consider one parameter subgroup of the group. So, well, this is just a convenient way to define a parabolic subgroup. Okay, so then because I have this, then I also have a parabolic subgroup here. So then the definition will be the following. E psi is semi-stable. If for every one parameter subgroup and reduction of P to the parabolic subgroup, but this reduction on some big open set U prime of U. So as before, I don't require the reduction to happen in the whole of U, only on some big open set U prime. Then, because I have this isomorphism, this reduction is going to produce a filtration of vector bundles on U prime. This filtration okay, so first I have the filtration only over U prime, right? But there is a unique extension as a torsion-free sieve filtration to the whole of U. So this is the filtration associated to this data. Because I have a one parameter subgroup. Then I have some weights, you're right. And they are important because now, and the condition is the same. Okay, so these are the objects that we are going to consider, and then we see that they have the three features that we observed here. It is not a principal bundle over the full X, but it has some singularities, some singular points. The filtrations that we are considering are torsion-free filtrations, and the degree has been changed by polynomials. And so this is why we call this a Gieseker stability condition for principal bundles over higher dimensions. Okay, so now the problem is that how to find the Harder-Narasimhan filtrations for these objects. Well, okay, so this can be also done for products of groups. Then I will have several torsion-free sieves and several isomorphisms. But well, just the notation gets more complicated, and so I will not do it here. So for vector bundles or principal bundles, there is a notion of if this is a vector bundle, well, maybe there is we know the notion of a Harder-Narasimhan filtration. So the Harder-Narasimhan filtration, if E is not stable, it will have a filtration such that the successive quotients are semi-stable and the slopes are decreasing. Right, so this is for vector bundles on over dimension 1. Over dimension n, there are two things that we can do. We can consider slope semi-stability, and then this is the same, but this will be a torsion-free filtration, or we can consider the slope stability, then the degree will be changed by polynomial stability. For principal bundles over a curve, Ramanujan gave a notion of a Harder-Narasimhan filtration, and it says that there exists a unique reduction, PQ, to some parabolic. Such that for every non-trivial character which is a non-negative combination, linear combination of positive roots. The following holds. So this is the translation of this. So here, or if you put here GLN, then its positive root will give you one of these inequalities. For curves, yes. Dimension 1, yeah, I forgot to put a 1. Yes. Yeah, a non-trivial character. Non-negative. Non-negative combination of positive roots. Non-negative. Yeah. There is a very nice construction of this. And well, also one can consider this in higher dimensions using polynomial stability, slope stability. But then the reduction only happens in some big open set. So this has been studied. And there is a very nice construction following ideas of Atiyah. And then it was done completed by Anshus, Assad, and Biswas. And so the idea is to look at, if you have a principal bundle, look at the adjoint bundle. Then for Mumford stability, for slope stability, there is a very nice property that the principal bundle is semi-stable if and only if the adjoint bundle is semi-stable as a vector bundle. So suppose you have a principal bundle which is unstable, then the adjoint bundle as a vector bundle will be unstable. Look at the Harder-Narasimhan filtration of this adjoint bundle as a vector bundle. Then you can prove that this filtration, in fact, is a Lie algebra filtration. It respects the Lie algebra structure. And working a little more, you see that this filtration comes from a reduction of a parabolic, and this is exactly this reduction. Okay, then, but for higher dimensions, this doesn't work because oh, yeah, I forgot. Well, I have to do something else. The associated levy is semi-stable. As a principal L bundle. Yes. This is the translation of this. That it's a sum and is semi-stable. Yeah, thank you. Okay, so then, but this is not going to work for higher dimensions, because for higher dimensions, if a principal bundle is semi-stable in this sense, then the adjoint bundle does not need to be Gieseker semi-stable. Then, well, one idea to obtain a Harder-Narasimhan filtration was to use the Kemp filtration. So use the GIT construction of these objects. And in the GIT construction, each object is corresponds to some point in some quad scheme. If this point is a GIT unstable, it will have some Kemp filtration, and this will give you some filtration. So I will just explain. Okay, so in the GIT construction, one has you have some well, first so you fix the Hilbert polynomials and so on. So we are going to consider torsion-free sheaves. with some fixed polynomial, and then you fix some large integer, and then you consider first the space of torsion-free sheaves together with a choice of bases. Then this depends on M. Then, well, this you compactify this in some Hilbert scheme. There is a natural, and then this gets some linearization. So to do this, there are now two main ways of doing this in higher dimensions: the Gieseker construction and the Simpson's construction. And the line bundle that you get is different, but at the end, the end result is the same. Then, of course, here you have the group GLN acting. And then, so here, I have to repeat, this is a projective variety, but then you are not interested in parameterizing these pairs. You want to forget about this, so you take the GIT quotient. So then, by the standard techniques of a GIT, you will take the semi-stable part, and and this will be your moduli space. Then you have to check, and this is not easy to check, that a GIT point here corresponds to a GIT semi-stable point corresponds to a point here, and but this can be done, and then Kemp this works in general in any GIT setting. If you have a point in some variety, which is GIT unstable, then there exists a unique one-parameter subgroup of a GLN. Well, up to reparametrization. In which mu q lambda divided by this is maximal. Well, here I didn't say, so the GIT, the Hilbert-Mumford criteria for here you apply the Hilbert-Mumford criteria for semi-stability. So this tells you that you have to look at the one-parameter subgroups, and then there is a quantity that is defined here that, well, I guess that most of you know, and now it is not important. This was explained in the lectures of Johan last week. And then you have to normalize so that then this is unique. So then the condition of semi-stability is that this mu is non-positive. If it is positive, it is unstable. And then you can look for what is the highest, so the maximally destabilizing subbundle, one-parameter subgroup. Okay, so then one idea that we can check is that suppose I have an unstable bundle. I put it in some Qn, choosing a basis, and then it will be unstable in the GIT sense. Then there will be a maximal one-parameter subgroup. This, so the Kemp will give a filtration of V. V, recall, is just this. So this filtration by evaluation is going to produce a filtration of E. Okay, I call this filtration the M-Kempf filtration because it depends in the choice of M. But for torsion-free sieves, one can prove that if M is large enough, then eventually this filtration stabilizes and you get precisely Harder-Narasimhan filtration. So this was done by my student Andrés Zamora, Alfonso Zamora in his thesis. So then Kempf filtration coincides with Harder-Narasimhan filtration. Okay, so now the idea is that if we have a GIT construction of principal row sieves, apply the same. But there was a difficulty that we were not able to prove that this stabilizes when M gets very large. Because we are considering some nonlinear things, then it is only piecewise linear, the functions that we want to maximize, and we were not able to do this. And so then for some time we forgot about this, and as I was saying, until 6 years ago, I came here and I learned about beyond-GIT, in which you can construct the moduli space without any choice. And well, in fact, I have already learned a little about this by the talk of Johan Heinloth in 2015 in Chennai, in the Congress, the conference in commemorating the 50th anniversary of the paper of Narasimhan Seshadri. Okay, so then, yes, let's explain. Just what I need about beyond-GIT. This is my Alper Leistner. Heinloth. So the idea is you have a moduli stack. Yeah, you can construct the moduli stack of this object. There is no problem there. You have a moduli stack, and then the idea is to look for some open set, which is going to be the point of the substack of semi-stable objects. I will call it this because it admits a good moduli space. Okay, so then in practice, how do you find these open sets? So there is a standard technique that is using numerical stability conditions using line bundles, and it goes as follows. First, I will introduce this object that already appeared in the lectures of Johan, or ET divided by C star. So this is a stack quotient. I have the affine line, and GM is acting by just a multiplication on the affine line. If you prefer this, the affine line is spec CT, and then C star is acting just by multiplication. This action has two orbits only. One orbit that corresponds to t equal to 1, and one orbit which corresponds to t equal to 0. The orbit corresponding to t equal to 1 is just the affine line minus the origin divided by GM. So this quotient is just a point, just the usual point. And here you have the 0 orbit. In the 0 orbit, Cm is acting, so a point divided by Cm or by Gm. As a stack, this is BGM. This is a stacky point. So just to repeat, in the quotient in the stack sense, the points of the quotient are just the orbits. So these are the two orbits. So there is an open orbit whose limit is the closed orbit. In fact, I think I have been told that this is a geometric representation of this. So this should be like the non-zero orbit, and in the center you have the zero orbit, which is a stacky point. So, okay, so then I define for any stack a filtration of a point. C on M is a map from this to M together with an isomorphism of this, and F naught, I call it the associated graded object. So this is a very nice construction that in the case of vector bundles, this data corresponds exactly to a filtration, and, but this is very useful because, for instance, if you're considering the stack of varieties, this will correspond to test configurations. If you consider the modular stack of principal bundles, this will be filtrations compatible with G structure, so reductions. And then the idea is that we have a line bundle on M. And then Z is semi-stable if for every filtration of Z, the following number, the weight of F pullback L over 0 is like this. So here, again, it depends on your sign convention. I use a design convention. So if you have a map from here to here, then pulling back the line bundle, you have a line bundle here. This is this. This line bundle restricted to 0 is a vector bundle on BGM. A vector bundle on BGM is just a one-dimensional space with an action of a GM. And this action is a weight, and then this weight should be smaller than 0. And then the great theorem that we use is that if Z is unstable, then there exists a filtration such that the weight, this weight, divided again by some norm is maximal. Again, filtration up to reparametrization, which means that the weights can be multiplied by some constant. Okay, so the idea is to use this filtration. If we have an unstable object, object to consider this filtration. And so we can check this first for torsion-free sheaves and then apply it for these objects. But there is one small surprise, is that in higher dimensions, we will have to apply this construction several times. Okay, so this is what I mean in an example. Suppose we are in P3, and P will be a point, C will be a curve, and D will be a divisor. And the toy example that I am going to consider is just the structure sheaf, then the ideal sheaf of a point, then the ideal sheaf of a line, and then the ideal sheaf of a D. Okay, so then the degree of this is minus the degree of a D. And well, it is easy to check that yes. Well, yeah, maybe in my notes I have a line, let's say a line. Yeah, yes. Point, line, and so on. Yeah, they are not necessarily. Yeah, this is the ideal sheaf of some line in P3. And yeah, they don't have to be nested. Or any curve. Yeah, but to fix an example, just fix a line and fix a divisor, which could be a hyperplane. Yeah, maybe to make this more concrete, I fix this. Then the Harder-Narasimhan filtration, the Gieseker-Harder-Narasimhan filtration of this sheaf. So the maximal, it will be first, you have this, E. Then you have this plus this. And then you have this, this plus this plus the line, and then you have E. So this is the first term, this is the second term, and this is the third term, and the total thing. X is a P3, yeah. This is easy to see. But then, if we take now I will run this program. If I run this program and I look at what is the filtration given by this F, it is just the Mumford, surprisingly, is just it will be just this and this. So in the first step, I obtain the slope Harder-Narasimhan filtration in this case. Okay, then I take the associated graded, which will be this plus this, and then on each piece, I run again the program. Then this will be in the first step. In the second step, I will obtain this filtration, and this I already had. So this is similar to what happens in the thesis of Andrés Ibáñez Núñez, that he has to consider successive filtrations. So first a filtration gives you a graded object, and then you look at filtrations of each of the objects. And then, of course, this eventually stops because of the dimension considerations. So it is very interesting because it looks like you are constructing the Harder-Narasimhan filtration, not the usual way. That the usual way is that first you look at the first term, and then if the quotient is not semi-stable, you look at the second term, and so on. Here you are doing by dimensions. First, you are looking at the leading term in the polynomials, so you are looking at the degree. Then once you have a filtration that with respect to the degrees, you look at the second term. The second term is looking at the degree and the second term class. Then the third one will look at the first, second, and third term classes until you get to the dimension and you finish. Okay, so then the idea is no, because no. This has nothing to do with Jordan Helder because Okay, so in the first step, this object is a slope semi-stable. And but then the filtration, but then it is not a Gieseker semi-stable, and the filtration will go with respect to the Gieseker stability. Okay, so then this procedure can also be applied to these objects, and the idea is that we will start with some principal bundle like this, with psi. Then this is going to give me some reduction to some G. Then here, this will give a filtration here. So then I will have some graded object here. Here, I will have a principal L bundle, where L is the levy of the parabolic. And well, here I will have, now I have a collection of isomorphisms with this. This is why I need to consider not only representations in GLV, but in products of GLV. But the idea is clear. And then I continue. So if this is not Gieseker semi-stable, I keep going, and then I will have a further. So this levy, I call it L1. Now I will have a parabolic of L1, and then the corresponding levy, I call it L2. And here I have more size. And then after n steps at most, this will finish. And okay. Yeah, I have an example here for the symplectic group, but I don't know if it is very illuminating. Yeah, so how much time do I have, or I am 3 minutes? Okay, so then I guess I can just put this example. So again, this is a toy example. E is going to be OX plus OX plus OX. Here I take the point, I take the point, and I take the line. And then the bilinear form is just a -1, -1, -1, 0, 0. Given by this. So then these objects are isotropic. So then in the first filtration, the first one parameter subgroup, well, I will describe the filtration. The first filtration that I get is just this and this. So I call this E1, I call this E2, E1 inside E2, inside E. This is isotropic, and this is the orthogonal. So then I have reduced to a parabolic that looks like this. The levy looks like this, and the levy here, I have the symplectic of dimension 4. Here I have a GL1. So then the first levy that I get is a GL1 cross SP4. And then in the second step, I guess, well, I just put O, 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 IP, IP, IL. So I had already this filtration. So then now I get this piece will be graded like this. Will have a filtration like this. And yeah, then finally the levy of this is a GL2 here. The second levy that I get is a GL2. So I had GL1. This factor comes from there. The second reduction to this gives me a GL2. And then what I get here is the Harder-Narasimhan filtration for this case. Okay, so thank you.
Questions? Yeah, Andres.
Microphone.
It's not really a question about the Harder-Narasimhan filtration, but about semi-stability. When is semi-stability non-empty? Like, are there some results like that? Like, I guess it could happen that it's just empty semi-stable locus, for instance, for the symplectic group. If you can, if you consider like distortion-free sheaf compactification, do you get non-empty semi-stable locus, at least in some cases?
Yeah, but again, but it is with some conditions, like a C too large. Yeah, Mr. Yeah, in particular here. Yes, no, but that is true. That here I haven't said anything about whether this is empty or not. And yeah, as Balaji says, there are some theorems that tell you that in the case of surfaces or very high second term class, it will not be empty. But yeah. So in general, you could be in a case, suppose potentially, I guess that you could be in a case in which there are no semi-stable objects. Then you take an unstable one, but then you can run this program, and then you will finish with some semi-stable one. Yeah, what I didn't say is that this as a GL1, GL2 principal row sheaf, it is semi-stable. But then this group is not the one that you started with.
So you can always find some non-empty semi-stable locus for a different group, for a levy. By taking
but you have changed the problem. Like eventually, you could get all the way to just the products of a GL1, and so this will just tell you that there are line bundles. No more than that.
And for Calabi-Yau threefolds, do you know some non-emptiness results, semi-stable locus?
Yeah, no, I don't remember right now. I don't know.
Thank you.
Yeah, what moduli stack of principal bundles do you have to look at? Doesn't your definition, it's going to depend on what the bigger moduli stack is, because you need to have the extra point, right?
Sorry,
yeah, in your definition, it depends on what the bigger moduli stack is. I mean, for a given point, in some moduli stack,
yeah,
this filtration and so on, that depends on having another point sort of attached to it in the moduli stack, right? So you have to decide what.
You mean
the point, the 0 point.
Yeah. So I am starting with just a moduli stack of a principal row sheaves.
What?
The moduli stack of principal row sheaves, and without any semi-stability condition. And
bundles, no.
No, principal row sheaves, meaning a triple like this.
Okay, I see.
Yeah, they could be bundles. Yes. They could be bundles. Yeah. So in particular, so what you expect is that there is a, no, that's true. Suppose you start with the moduli space of a principal bundles, right? Then, yeah, it is true that to get the proper objects at the end, so you have to.
Is there a way of controlling, how big that has to be?
I don't know, but so what is true is that this compactification will depend on the representation that you choose. That is definitely something. So
does that mean that the Harder-Narasimhan depends on the representation?
Yes. That is true.
And is there some sort of stabilization that as you get bigger and bigger representations, somehow there stabilizes?
I don't know. And also maybe there could be some uniqueness results if you will assume that the term classes are, so that the characteristic classes are vanishing. They are maybe, maybe they will be bundles, and maybe the filtrations will be filtrations by bundles. So the same thing that happens with vector bundles of a vanishing rational term classes. If you are in a projective variety, right, then if it is semi-stable, then it has to be a vector bundle. And if it is there is the Jordan-Helder filtration, that one that is locally free. Yeah, so maybe there are some nice things if you assume first, so the term classes to be the vanishing characteristic classes. But in general, here you start just with one group. Then with this group, you consider the moduli stack of a principal bundles. And then to get the compactification, you have to choose a representation. And I don't know how the compactification will depend on the choice of a row. In fact, maybe one could take like some direct sum of all representations in some sense of a.
I mean, is one part of the criterion that you want to have a bigger stack with the property that the coarse moduli space is compact? Is that?
Yes.
Saying? Okay.
Yes. Yeah, that's true. And this bigger, and then I understand. So you're right. So this depends on the bigger stack where you are taking the closure, so to speak. Yeah.
More questions?
Yeah, I have one question. So if we take the moduli spaces of flat G connections, and then the graded objects F0, is it coming from the opers sort of things? It's coming from G opers or?
But so sorry, so you start with a representation?
No, it's just the connections.
Connection, okay, just the connection, flat
G
connection.
Okay. So is it the graded objects F0 filtration is like it's coming from some sort of opers or?
Yeah. I don't know because here we are considering just we are not considering a connection, but maybe if you fix some Hermitian structure and then you consider the connection, I guess that you will get something like that, but I don't know.
Okay.
I don't
Questions?
know. Also, you have to be careful also because the correspondence between stability and existence of connections, this uses Mumford stability, not Gieseker stability. So then if you want to get something like that, then you have to go back to slope semi-stability. And then for slope stability, you already had the slope Harder-Narasimhan.
With the stability conditions that we have seen, like higher dimension, sometimes, so the original Ramanujan one, so
Yeah, so Ramanujan first fixes the parabolic and then takes a character of the parabolic. However, in the others, I mean, it's equivalent, right? But you can also first fix the one parameter subgroup, and then that determines you a parabolic.
Yeah.
From the beyond-GIT point of view, it seems like the fixing the character, the co-character, and then the parabolic is like the more natural thing.
Well, no, but in Ramanujan, so for the definition of stability, yeah, well, I guess yes. Maybe you can translate things, and then you will get also the other point of view. Yeah, just doing some Lie algebra or some Lie group theory, you can translate between one parameter subgroups and weighted parabolics.
One question. So the result is that emptiness, when M, the number you chose, is very big, is giving you the same filtration? Or
I don't know, but that would be something to look at. Because so we just use the filtration given by beyond-GIT to give the definition. But something is true that now that we know what is the filtration, maybe we could be able to show that it can be gotten also by the Kempf filtration for very large M. Because yeah, it is not the same thing. So when you have a filtration that keeps changing, if you have a guess of what is the end result, maybe you can show that it goes there.
You said it's stabilized for each sheaf. So.
Yeah, for torsion-free shifts, yes. For torsion-free shifts, yes. But for principal bundles, we were not able to do it. But yeah, that would be interesting. That now that we know what we want to get, maybe one can show that.
No questions? Okay, then let's thank Tomás again.